Ladies and gentlemen, welcome back to this afternoon's session. If everybody could just take a seat, please. So, thank you very much. Unfortunately, this afternoon's moderator wasn't able to attend, so very kindly, Richard asked me if I would stand in and do that, so I apologise. I shall do my best. Thank you, of course, to CBMM for organising, and to Beta Technologies. Very well organised event, obviously. I think the attendance shows the credibility of the event and the topic. Thanks to Lisa from the Brazilian Embassy, of course, for arriving. Thank you to Jane Evans from Beta for all the last minute efforts, and I know there were quite a few of those, and also for very kindly asking me to stand in this afternoon when I walked in this morning. So thank you, of course, to all our speakers, especially Professor Whittingham. I would say for me, it's amazing to share a stage with many of you guys and a Nobel Prize winner. Really great to be enabled to be here. So what I would also say is I don't have a PhD. I'm therefore somewhat overawed by our speakers and guests. Worse in this audience perhaps than no PhD in this setting. And forgive me, I'm an engineer, not a scientist. And I'm a power electronics engineer by background, but Professor Whittingham did say we need PE engineers, etc., and we need a lot more of them. So that makes me feel somewhat better. We also need to scale, industrialise, and commercialise the technologies that we're talking about. So we need engineering business people. So I kind of feel I do have quite a good reason to be here after all. So I look after business development and client project delivery. I'm the commercial director at UK BIC. UK BIC is for those of you who's not familiar with it, is a UK facility funded initially by the UK government, which enables third-party companies open access to what is a mini gigafactory to mature, scale their technologies and prove them at scale before having to make the large investment in plants for themselves. Get them over that valley of death, if you like, between technology readiness level, maybe 5, and real world production. So design for manufacture, prove at scale, and even manufacture for a short period in that way. So we work with a lot of companies in the UK. We only have 3 that are public domain so far, but we've had 32 contracts so far. 11 of which are already closed out successfully. I would say as well, we have 2 standard cell formats which we've developed as platforms for the industry. So we've got a 21700 cylindrical and a 300 by 100 pouch cell, the standard PHEV size, if you like, of cell, which we use as a platform, and we can integrate our clients' chemistries into those cells, again, to prove technologies at a mature enough level that end users, OEMs, can buy in, bridge that gap so that investors then see a technology at the right maturity to go forward and enable the development companies to invest further. One very last thing, Professor Whittingham did talk about the Binghamton Mini BIC. Thank you very much for calling it Mini BIC today, Professor. We did have a chat, so Stan did call me. I was very honoured to be called by Stan when he was talking about this proposal, and we provided a letter of support for that, which you were successful with. So congratulations on that as well, and I look forward to hopefully working with you more, as we intend to put something similar together in the UK as well within BIC. So I'm sure there's good opportunities to collaborate. So enough. We've got 5 excellent speakers. Our first speaker, Rahul, needs to leave for an afternoon flight. So we're changing around the order a little bit. And we'll have, is Rahul, Rahul is back here. Yeah, so let me just introduce Rahul. He'll speak for 20 minutes, and then we will have a short 2 or 3 minute Q&A session before Rahul needs to leave, and then we'll carry on through the other speakers and have Q&A, a full Q&A at the end. So Dr. Rahul Fotedar is from Morrow Batteries in Norway. He's Chief Technology Officer and was co-founder of Morrow. He has a master's degree in chemistry from the Technical University of Munich and a PhD specialising in battery materials from ETH in Zurich. Previously worked as staff scientist in the Institute of Technology near Oslo, where he pioneered research activities in the field of rechargeable secondary batteries. In 2013, he co-founded Graphene Batteries AS, startup focusing on developing technologies primary for heavy metal-free batteries. And prior to joining Morrow, he was working for many years as an expert in advanced cell technology in the Hilti Corporation, leading activities on developing and industrializing differentiated cell technologies. So, Dr. Rahul, sorry, Rahul, please, please, thank you.
All right. Okay, so first of all, thanks to CBMM for inviting me to speak here and to represent Morrow. And it's also an absolute honor to have the stage together with Professor Whittingham. All right, so I don't have much time and I have not practiced these slides, so I'll just rush in. Okay, yes, one slide back. So Morrow was basically formed or founded, I think it was summer of 2020, and it was founded on two ideals. And I like to speak a bit about our company, and then I'll come to the technology bit. So I want to give you an introduction of who we are and what we are doing in Norway right now. So Morrow, as it was founded, it has these two big pillars on which it is founded. We want to make the most cost-effective and sustainable battery cells in the world. And how do we do that? I mean, especially being in Norway, which is not a cost-effective country per se, we will bring the cost down using technology, which is a big part, and that's why I'm here, and that's why we all are here. We'll do integration. We'll go up vertically upstream integration. We'll make some of our own powders. We want to scale out all the costs, so we don't want to build subscale that somebody builds a bigger factory than us and just scales us out. And we want to run those factories at a very high level of operational excellence. So that's how we'll approach the cost bit. And the sustainability factors for us are very important. It's the climate impact of what we are doing. We don't want to create a solution which is itself a problem. A lot of people are asking if these electrical cars are clean itself. And then the social impact of what we are doing is very, very important. So these two things were actually the founding kind of grounds of the company, and that's where we position ourselves in. So that was 2 years back, and this is where we are right now. We have now close to 130 employees, not 110, 23 nationalities. Our headquarters is in Arendal, which is south of Norway. We have a small office in Oslo. We have a sales office in Germany. We have another labs in BRC in Grimstad, which is a place very close to Arendal. We are working on 4 technologies, 4 products. I'll get to that. And sorry, I can look here. And we are targeting different market segments, and I also get to that in a second. So this talk is not about so much about fundamental research per se. It's about how do you, it's more about the entrepreneurial hustle. How do you actually create a company where you need to bring a lot of different expertise together, technical expertise, operational expertise, financial expertise. So we have managed to assemble a team of quite qualified people who have done significant things in their professional career. And I think that is important. This leadership team will enable us to deliver our kind of really massive goals. And we have also in the past 2 years have been, we are lucky to have some really well-known investors such as Siemens, such as ABB to join our journey as investors, and Agda Energy, which was one of the founding investors, a big utility company in the south of the country. So that basically provides us the background on through which we kind of go forward. So Morrow, just so that you understand the context, we basically are looking to serve 2 markets. One market is the ESS market, the energy storage market, and the second market is the mobility market. The mobility market is really the EV market, which is the light mobility, and the ECV market, the commercial market, the trucks, trains, marines, you name it, where the requirements are a bit different. Very often you need higher cycle life, etc. And of course, I mean, we all know that the demand is really booming. And the big question is that are we going to produce these cells? Are we going to import these cells from Asia? Who's going to be the kind of who are going to be the main players kind of serving this market? So that I think the demand part is not a question. The question is the capability of how are we able to kind of address that demand. But this is These are the three market segments we are going to address with our products. All right, so this is a slide I'd like to take a minute on. So a lot of people ask us this question, hey, how can you make new technology and you have never been in mass production, how would you be able to deliver? And that's a very valid question. And this is something which has been touched by a lot of people. Actually, developing product is one part of the question or the equation. A much more complicated thing is to develop the capabilities to produce that product in a manufacturing environment where you basically have to produce batteries at the speed of potato chips, actually, with almost no defects. And this is no easy job. And like I said, we want to develop next generation technology, but we still have the humility that we think we need to understand how do we do mass scale manufacturing. So we are addressing this whole adventure, if you may, in two stages. In the first stage, we would go with more established technology. We have LFP and high nickel NMC for the main markets, which I told about, where the product development is not easy, but it has been done before. That wheel has been invented, it can be reinvented. And then we focus on actually manufacturing. We build that capability of how do we mass manufacture these cells? How do we quickly enter in this marketplace? How do we kind of get our space in the whole ecosystem? And then by building stone on stone, that kind of analogy, we want to transition from our Gen 1 technology to our Gen 2 technology, where we would basically go to LNMO. I'll get to that in a second, and different variants of that, which we believe would take us to this sustainability and cost target, which I was talking about before. But this is going to happen in different stages. And hopefully we are able to produce these Gen 2 technologies by the turn of this decade, and then go forward and make more factories and or license our technology outwards. All right, so again, so these are the 4 products we are actually developing currently. I like to say the Gen 2 technologies are more like technologies and not products so much, but the Gen 1 are quite mature products already in our portfolio. We already produced an A-sample LFP cell this summer. It has passed all the UN tests. It's already with many of our customers who are currently validating that cell. And the NMC high nickel cell is in development. I think summer next year, we'll have the A-sample of that cell. So that is a Gen 1 technology. And here, like I said, the focus is to be fast, but good enough so that we can come to the market as soon as possible. But where we are really investing a lot of our own internal bandwidth is our Generation 2 technology, the LNMO technology, where we are focusing on 2 different products. One is LNMO graphite cell, and the other is the LNMO XNO cell. XNO has niobium inside it, and that's why I'm here, where we're working with Echion, and I'll get to that in a second. But this Gen 2, the whole idea of developing the Gen 2 cell has been that we don't want to do it alone. We want to create this partnership network, and we have created this very extensive partnership network where we work with suppliers, component providers, and actually both of these cells are now being developed. We have like a marquee customer for each of the cells. We have a very large car company working with a graphite cell with us, LNMO graphite, and a very large ESS company with whom we are developing the LNMO X cell together. And they have much longer timelines, and we are quite confident that we'll deliver on those cells. Now, many of you would ask, okay, why should we do the LNMO technology? And I think this was talked a lot in this morning, that nickel and cobalt are problematic materials. Nickel is, the supply is too tight. Cobalt is fundamentally limited. There's child labor problems to that. And if you look at the battery breakdown, the cost breakdown, in essentially, you cannot make the battery cell cheaper if you don't make the materials that go inside cheaper. And if you really want to kind of democratize the use of batteries, you really have to find these ways to do that. And one of the big kind of push which is happening in the whole development kind of realm is to go from cobalt and nickel to manganese-based materials. And rightly so, manganese is much more cheaper and much more abundantly available than nickel or cobalt. And amongst all the manganese compounds, our favorite is the LNMO, the spinel LNMO. And this is the cost breakdown. You see, just on the material basis, you have 50% less less cost, which translates to somewhere between 20 to 30% on the cell level. You also don't need lithium hydroxide as a material. You can work with lithium carbonate, which is much more widely available. And I also like to say that we would not only make the LNMO-based batteries cells, we'll also actually go into powder production of LNMO itself. So we'll also vertically integrate upwards and build full-scale factories for LNMO material itself. All right, so again, to stay on the theme of industrialization, I think it is very difficult to overstate the complexity of going into mass scale manufacturing. And so what we have kind of envisioned and what we are trying to do is to build this whole a kind of an ecosystem of facilities. We call it the Morrow Industrialization Center, where we have a research center where we can do component research. We have a development line where we can build final format cells. We have a gigafactory actually, which we feel is like our kind of a launch pad towards making larger gigafactories. And all of that is required, and a lot of infrastructure and a lot of knowledge is required that we are able to train ourselves to be actually kind of compete with large companies such as Panasonic, such as Samsung's out there who have built this learning curve over decades. And this is something we are actually in the process of doing. So we have this is our battery research center in Norway. This is the largest battery research center in Norway. Currently, the building is almost finished. We would be moving our researchers inside April of next year. About 100 researchers would be able to work here. And yeah, so we would be doing component development in this center. This is actually placed within the University of Grimstad, which is 10 minutes from our factory. So we also wanted to benefit from the academic partnership between the battery groups in that university and our factory, which we think is very important for actually even training staff as we need, which we would need as the company grows. So this is a very important component of our kind of long-term strategy of how to build battery competence in our company and in the ecosystem. The second bit which we are building is what we call the customer qualification line. This line is being built in South Korea, because the building for hosting this line is not ready in Norway. But this line is fully capable of producing final format A and B sample cells. And this is actually the site acceptance test is ongoing right now. And we would move in full production January and run this operation in South Korea for a year before packing it down and moving it back to Norway. And last but not the least, we are building the first factory, which we call the Battery Cell Factory 1. It's a 1 gigawatt-hour factory. This is also in construction right now. I think the walls are up, the equipment is ordered. The planned date for the first cell to be produced is end of next year, and the full-scale production should happen the summer going forward. And one of the things which I like to say is a lot of people ask us, is your factory future-proof enough? And so our technology roadmap is not so much production focused. We want to have the capex investment kind of be ready for the next generation technologies as well. So the same factories are able to, or the same lines are essentially able to produce all the 4 products we have. And so that the investors who are investing in this, they see that these assets are actually relevant in the next years to come as well. Good. And the plan is to use the 1 gigawatt module to learn and then kind of build 14 gigawatt hour modules going forward. And that is what we have, the land and the power and the water available in the site we have in southern Norway. And then we see what happens next. All right, so that was the background. Now I want to jump in what we are doing in the LNMO X space. So like I said, we have 4 different products. They have their own life stories, their own development teams. But the LNMO X is one of the products where we use the niobium-based anode. And we have, like I said in the beginning, we have this very strong partnership-based approach. We are working with Haldor Topsoe, a very large Danish company, which has been pioneering this spinel LNMO since last 10 years. They've done a lot of beautiful fundamental work on that, and they are providing us the material. And the XNO material we are basically receiving from Echion, a Cambridge-based startup, if I may still call it. Very, very, very interesting materials, and together this makes this very beautiful chemistry, which we are kind of developing in our facilities. So what you have, and I mean, I'm sure John is going to follow with me and explain you all these things with different more data curves, etc., is that you get fast charging capabilities, you have a sustainable system, the safety is very high, and you have low temperature performance. Things our customers are looking for in different applications. And by kind of pairing these two innovative materials, we're able to deliver on that. So as you see, this graph is an interesting graph in front of you. So we have like two axes, right? If you look on the horizontal dotted line, you have to be above that energy density to be viable for mobility. And if you then this vertical dotted line, you need to be more on the right side of that axis to be viable for heavy duty transport, where people are not looking for few thousand cycles. They want as many thousand cycles as possible. So currently you have basically a landscape of such chemistries. You have high nickel providing some high energy density, then you have LFP straddling between these two worlds. And then you have NMC LTO systems, which can provide a lot of cycle life, but have much low energy density. So LNMO XNO basically is this amazing product, which will have the energy density of LFP battery cell and a cycle life, which has to be for no reason less than an NMC LTO cell. So very, very attractive product and a product which all our customers actually want to have. And I'm very confident that we'll deliver on that product. So this is the first cycle curve. You have a 3-volt cell, unlike a 2-volt or 2.2-volt cell, because you have this high voltage cathode paired with a high voltage anode. And this is also a good thing, right? For a lot of battery pack developers, module developers, they like to see a chemistry which is at a high voltage already, so they don't need to put so many cells in series. And so this chemistry is able to deliver that, this high voltage. And so again, I want to emphasize how are we able to do that. So Morrow has a big team. We are already 100+ people in the R&D department, but we can't do this lifting ourselves. So our whole strategy is that we want to work with our suppliers together. So this whole supply chain for the next generation has to kind of mature as the technology is matured. So we are working with Topso, we are working with Echion, we are working with CellGuard, we are working with a bunch of electrolyte partners, binders, because every single component has to be ready for this high voltage system. You don't have the binders in the ceramic separators are not stable at 4.7 volts. So you have to basically develop new generation of separators to be able to kind of tolerate these high voltages. And what we are doing is basically working as a central cog of this machine, providing, for example, an additive manufacturer a very high quality material so he can develop his additives, electrolyte manufacturer a very good system. So all of them can do their individual iterations very fast on a very high quality baseline system and provide us feedback. And then we send the feedback back to them. So by doing this in this kind of extremely cooperative manner, we want to accelerate this development. And that's, in our opinion, the only way to do it in the timelines we are envisaging. Again, we have a very close partnership with Echion. They have a phenomenal material. We signed a supply agreement with them last year. So that is basically the material we are currently using in our cell design. Very happy to have that partnership. We are working, something we are doing is very, very fundamentally very interesting, is that electrolyte development is a huge part of high voltage systems. And so there's really an amount of solvents, additives, salts, and the combinations are so many, it's very difficult for us to basically conduct as many experiments. So now what we have done, we have partnered with the artificial intelligence company Citrine, which basically takes data from and metadata from our testers, and then they have train their models, and then basically helps us screen the electrolyte. So we get less and less actual experiment to do, and we are able to basically accelerate the development of that. I don't know how is it, the jury is out. We just started this partnership. Hopefully we'll have great results next year through this partnership. Also, we signed a development agreement with CellGuard, where CellGuard is basically developing kind of a bespoke separator for us, which is able to withstand this high voltages, is able to wet at. We have propylene carbonate in some of the formulations, which is very difficult to wet if you want to use ceramic coated separators at that voltages. So again, referring to the fact that we don't want to develop the components ourselves, we want to do the cell development and integrate those components together back in Morrow labs. So this is a slide I showed last time of some work we did on this sample, we started early last year. We were R1 sample, very low loadings, very low active material content, and very quickly we have actually taken it from R1 to R2, where we're looking at the loading levels, which is relevant for our 400 watt per liter target. We are already building pouch cells at that loading level and at a higher active material content. And yeah, it's actually looking surprisingly good. So nothing to complain about. Going forward, we have an extensive development plan of what would happen. We made the coin cell. We have made the second coin cell. Actually, last month was the first 1 amp hour pouch cell, 19-layer pouch cell made in our labs. The next step would be a 40 amp hour pouch cell, and we're already targeting a 10 amp hour prismatic cell next summer based on this technology. So extraordinarily aggressive, but so far we don't see why should we not be able to achieve that. Everything seems that we have it in our target side. So again, this is again visualizing the same thing that we started with the small lab scale coaters, then we tried to coat a few meters of electrolyte, then we went to a slightly bigger coaters, and where we are actually right now, we're coating tens of meters of electrode of XNO and of LNMO. And next month, we'll already start coating kilometers of electrodes for both of these systems so that we are able to build these larger cells, which I talked about. And yeah, so we are right now in this few amp hours to 40 to 50 amp hour zone. The target is to build a 100 amp hour plus BEV2 format cell by next May, June time period on our line in Korea. I know I'm running out of time. This is the timeline. So very, very psyched. I'm happy about this system. I hope we can bring that to the market, and it really outperforms the existing technology in almost all domains. So thanks a lot for listening. I'll stop there.
Thank you very much. You just stay up on stage for a moment. So Rahul has to go away to catch his flight. So we've got a couple of minutes for some Q&A. If you'd like to do that now, I'd just like to say what a beautiful place that looks to be. So I'm sure we're all going to get invited over to spend a little.
Absolutely, absolutely.
Any questions, ladies and gentlemen? There must be some. So I have one for
sure, please.
You say you're starting off initially with a small scale line. Many of us, well, obviously with piloting, etc., etc. You're doing that overseas. You're doing your acceptance tests, and then you're going to run it actually overseas as well.
Yeah.
For a period of time. Though.
So I mean, this was like a decision we made last year. So you need to be able to run like a significant scale pilot line. And we bought most of the equipment from Korea, from different vendors in Korea. So we just thought, let's kind of put it together in Korea. We rented a big dry room in Korea. So we're going to run that line in Korea. So our operators are going to run that line. We have actually a whole team there. And that basically is all towards accelerating the product development cycle. And they would also learn it because, you know, a lot of the engineering and machine knowledge is not in Europe, it's really in the Asia. So it's good, like, you know, when we have that line transferred back to Norway, we already have played with that line for a year. So we know what can go wrong, what can go right, and that actually accelerates the whole thing.
So you have your staff actually over on the line?
Yeah, absolutely. We would run that.
Excellent. Sounds very good. Any other questions? Jen?
What would you say is the biggest challenge, has been the biggest challenge getting to where you are now, and what do you foresee is the next biggest challenge getting to the 14 gigawatt hour facility?
Ooh. I think it's the biggest challenge has been, I mean, you have to demonstrate, I mean, to get investors to basically kind of, I mean, a lot of money has gone behind it. So $300 million has been spent in basically creating these facilities and product development, right? So, I mean, we have been lucky that we have some good investors in the beginning, but we still have to demonstrate that as a novice, we can actually deliver, right? There's a lot of question marks about all these gigafactories being announced everywhere. Would these people actually turn up? Would they be able to actually make the products? And I think the jury is out, right? We have not actually produced ourselves. We are building the capabilities, we are doing the hard work, and I hope that we come out at the other end being able to deliver. It's not easy, it's quite overwhelming, but we have to do it, so we are doing it.
Just one more. Any more questions? No more. Oh, we have.
Claire has a question.
I've not looked at the LMNO for many years, but one of the issues is if you go down to too low voltages associated with the manganese dissolution.
That's right.
I'm just wondering how you feel the XNO versus graphite influences that, and what are the electrolyte strategies or coating strategies on the LMNOs? Just
very good question. So I mean, like I said, the LNMO graphite system is far more difficult actually compared to you have manganese dissolution, and then it blocks a lot of sites at the low voltage, it deposits there, reduces. So we don't get anywhere close that cycle life that we're seeing with the XNO system and the graphite system. So and we're looking at all kinds of classical strategies, from having some sacrificial additives in the electrolyte, which can be oxidized when the thing is happening, to coating, to artificially produce SCI. So the LNMO graphite system is going to be not easy. And that is really the moonshot in our company currently. But the LNMO XNO system, on the other hand, it actually is working. We're slapping them together and this thing is working. So.
And do you think the separators is going to play a role if you're putting ceramic separators?
We have the tri-layer polymer separators right now in our pouch cells. They are doing well, but many customers want a ceramic coated separators for passing different safety tests, and then you have vetting issues, etc. And then you need some development happening on the separator side. And we haven't done that yet, but with the CellGuard collaboration, we hope that we'll have some ceramic coated separators that can also work.
I'm sure a bit of niobium on the LMNO will do the magic trick you need.
Okay, thank you. Thank you very much.
Thanks a lot.
Thank you very much.
Thanks a lot.
So, thank you, ladies and gentlemen. So next, and it was already alluded to already, so we have Dr. John de la Verpilliere. I can never say it right, John, I do apologise, from Echion. So John's co-founder and chief executive of Echion. Prior to co-founding Echion, John was at University of Cambridge. He was a Nano DTC Translational Fellow, which I had to look up. So that's, I understand, PhD training research in nanoscience and translation into technology. Fantastic. Yep. Okay, so bridging the gap between academia and businesses. Following graduate studies in École Centrale Paris, he investigated novel battery materials during his PhD at Cambridge Engineering Department. And John is a recipient of multiple scientific and business awards, including Forbes 30 Under 30 Europe.
That's a piece of that.
Wow, fantastic. So thank you, John. Over to you, sir.
Okay. Thanks, Ian. And as we are on my biography, I'm not a doctor. So I started my PhD actually here in this very college, King's College, in 2013. Did it for quite a few years, but then decided that entrepreneurship was more fun. So never completed. I'm not a doctor, which is why I'm not the CTO. Alex is. But yeah, no, it's great to be here. So King's is quite a special place for me, because that's where a lot of Echion started. Actually, if you look on the internet, there's a picture of me in 2016 in the front court receiving a prize for the second place for the King's Entrepreneurship Prize 2016. And on these pictures, I look quite young, very happy, and very stupid. So here we are, 5 or 6 years later. I'm less young, I'm a bit fatter, still very happy, and probably still quite stupid yet. But at least we have a company and a product. It's not an idea anymore. We have Echion Technologies, and we are a supplier of the anode material that Rahul was talking about in the previous talk, XNO, for mixed niobium oxide, which is a new class of anode materials that enable lithium-ion batteries to be safer, faster charging, and with longer cycle life. So this morning we've heard beautiful lectures about I think really what happens at the fundamentals at the material level. So here we want to give you, following Rahul's talk, an overview of what's happening at the industrial level, on the commercial level. So that's what I'll be talking about today. I think Rahul alluded to it, but just want to make clear the market that we target with XNO. So XNO is not primarily targeted at electric vehicles or energy storage. It's not targeted at markets that want high energy density or very low dollar per kilowatt hour. Instead, it targets markets that you can see some of the applications on this slide. So it's markets that are really driven by total cost of ownership, and they want high power. So quite a lot of these vehicles are quite big, and you need a lot of power to get them moving, or they need to accelerate very fast, so you need power. Quite often you want high utilization. So if you have a very expensive capital asset like a mining truck, you want it to be in use all the time. You don't want this very expensive piece of equipment to sit there doing nothing, recharging the battery, because that downtime costs money. So you want fast charging. Safety goes without saying. If you have this very big equipment with very big batteries, it needs to be safe. And the long life is also a feature of many of these applications. If you design a train, a locomotive, you want it to last between 10 and 40 years. So that's an incredible number of cycles of charge and discharge. So if you have a longer cycle life, you can really minimize the total cost of ownership. So in the grand scheme of things, you could call them niche markets. If you compare to the size of the passenger car market, they're small markets, but the battery market is so big that even the niche market is in absolute terms quite sizable. So that's at least 100 gigawatt hour we estimate for these markets. That to summarize, that's heavy duty commercial and industrial e-mobility, and that's where XNO has a great value proposition. So what is XNO? So XNO, as I said, is an anode material. So here you have a simplified schematic of a lithium-ion battery. So 98% of lithium-ion batteries on the market today have a graphite or carbon-based anode, which limits the safety, the cycle life, and the charging speed of the system. So we replace this carbon-based anode with the material that we've developed, XNO. So XNO stands for mixed niobium oxide. So Professor Gray this morning gave an example of WNO. So Echion has another X. We don't, another element which is mixed with niobium. We don't disclose what the X is. But it's generally the same class of material, and I'm sure we'll hear from TOSHIBA later, who use titanium niobium oxide. So it's this general class of material. So the Echion material, which Morrow is using, XNO, is covered by 13 patent families, 7 of which have patents that are already granted in the UK or Europe, and you have a little SEM picture of the material here at the top. What does it look like in a cell? So I think it's interesting because Rahul's graph had different dimensions on it. So here we have energy density on the y-axis, like Rahul, but on the x-axis we have the maximum rate of charge and discharge to maintain 80% of the original capacity, whereas Rahul had cycle life. So I think it's interesting because it's a multi-dimensional problem. It's complicated, but what you can see on this graph here is that graphite has very good energy densities, and here we're looking at a subset of power cells. You have some energy cells who are really much higher up this graph. But as soon as you start to have requirements in terms of fast charging, the energy density of graphite-based cells dips dramatically and is fundamentally limited in practice after some point. If you fast charge a graphite cell much faster than this, you'll hit problems in terms of safety or cycle life. So the one technology on the market today that can fast charge that can fast charge and have a very long cycle life is LTO, of course, which is that blue bubble in here. And TOSHIBA is, of course, one of the world leaders in LTO. I'd say one strong limitation of LTO, however, is the limited energy density, and so that's where XNO comes in. So with XNO, you can have the same fast charging capability, safety, and cycle life of LTO, but with close to double the energy density. So this, and that's the green bubble. So it's a bubble and not a single point, because it all depends how you put the cell together. So we have one anode, but then you can match it with different cathodes. You can use different loadings, different cell formats, and so on. And depending on the C rate and the life you design, you end up with a spread of performance. So Echion's business model is that we supply the anode, we supply the powder, and then it's up to the cell manufacturer, like Morrow, for instance, to put the cell together and reach the performance that they need to convince their own customers. So here on this graph, you can see a few examples of cells made by customers, which we can talk about publicly. So you have this kinetic pouch cell here on the right that is designed towards high power, high pulse power. In particular, you have these high electrolyte pouch cell on the left. It's a small pouch cell made by a small cell manufacturer in Japan, which has reached a very good energy density, and I'll show it later. Forecasted for 12,000 cycles of cycle life. This pouch cell. And finally, in the middle, it's the cell that I have a dummy here, so you can touch it. It's a fake one, but it's a 4690 cylindrical cell made by EIS in Germany, and the development of that cell was subsidized by Innovate UK, who's in the room. Thank you. Yes, right. Bit more results. That's a scoop. I think it's the first time we disclose these results of these EIS cells, and we'll communicate about it. I think we're very happy about the results. It's a very interesting cell design. It's a tabless design, which enables very low internal resistance for this cell format. So we're getting very good rate capability, energy density in excess of 300 watt-hour per liter, 100 watt-hour per kilo, and the cycle life is in progress. I think you can just about see on this graph we're reaching 900 cycles. So for the first generation, we estimate that this will reach 2,000 cycles. It's not it's a very good start for a first generation prototype. It's great. We think we can do better, and I'll talk about it later. Yeah. And this cell is now available for sampling by OEMs who are getting in touch with EIS. This slide is entitled "About Life" because I think it's basically a different approach to the question of aging and degradation than the one we saw this morning, which was really focused on the fundamentals at the material level. So here we're showing a selection of results from that comes from our partners and customers of different cells that have been made in different formats and reaching different performance in terms of cycle life. So it's important cycle life because typically in a sort of industrial setting, it tends to be the thing that takes the longest to optimize. For one reason, because when you are targeting 10,000 cycles of cycle life, it takes a long time to test it. But also because aging and degradation is such a complex phenomenon that yes comes from the material itself, but also from all the other components of the cell who all talk together. So yeah, you can see a few examples. As I said, the high electrolyte pouch cell is still cycling and is on track to reach 12,000 cycles, and you have other examples. I'd say as a rule of thumb, most of our customers target 10,000 cycles of cycle life, and we have a team at Echion who can support them to really do post-mortem analysis of the cells and understand the fundamentals to help them get there. Talking about customers, so again, our business model is really to sell that powder to cell manufacturers. So there's about 30 cell manufacturers worldwide who are at various stages of developing products, so cells based on XNO. So typically, they'll start in the lab with a coin cell, and as they progress, they'll go towards larger and larger formats. So I knew that Rahul would be in the room, so of course I put the Morrow on here because it's public. It's public that we work together. Yeah, I'll echo what you said. We're very excited about the LNMO XNO system. We think in terms of the energy density, temperature stability that you get, and most interestingly, yes, the voltage profile. I think it's a very good, very unique system, and that it can really reach the top of that green bubble that you show that I showed in the previous slide. So beyond cell manufacturers, we also engage with pack makers and OEMs, but that's not to sell to them. We don't sell cells, but we help create the market for this new technology. At the end of the day, we want to sell powder, and in order to sell powder, someone needs to have niobium-based cells in their vehicles in high volume. So we are evangelizing, I would say, and this cell here is a tool to evangelize and do marketing to these OEMs. They need demonstrator cells to test in order to understand the benefits, and these EAS cells will be tested by most of these OEMs whom I can't name. I'm sorry. Yeah, an example of that is of such an interaction is a project we have going on with the ChargeOn consortium. So ChargeOn is a consortium of some of the world's largest miners. So you have Vale, BHP, Rio Tinto, and so on, who are in this, and basically put out a call to come up with the best solution to electrify mining trucks. Okay, I'll be quick. So in short, electrification of mining truck is the perfect application for XNO. You need very long cycle life, you need fast charging, and you need high safety. And we've partnered with a whole supply chain, with a cell manufacturer, with pack people, with power electronics people, with system integrators, in order to come up with a solution which actually won, and we're able to demonstrate for now only on paper that with this solution, we can reach record low total cost of ownership for this application, which is what they want. So this is in the this project is now in the early stage of proof of concept, where and hopefully we'll soon have electrified trucks running based on XNO cells for the proof of concept, and go from paper to reality. Quick word about the roadmap of Echion. So as I said, we started the company in 2017. We did not start with Niobium. We went there later. We started with the first generation of material, which was already quite good in terms of, our first Niobium-based material was quite good, but had problem in terms of the voltage profile of the material, and we by the time we realized that by making demonstrator cells, going to OEMs, showing the voltage profile, and that's where we got the feedback. The voltage profile is not good. It's too sloping, and that's due to XNO. So not all niobates are created equal, and depending on which X you choose, you'll get different properties in terms of voltage profile, energy, power, gassing, processing, cost, freedom to operate. And so over the years, this 3 or 4 painful years, I think, we've iterated, close to 1,000 different formulations to come up with what we have now in our XNO3. So the story doesn't stop here. XNO3, of course, we're working on making it better and better and better. A lot of it is happens at the aging and degradation end of things. So we have really team of very good scientists to understand some of the fundamental phenomena that we talked about this morning. We also have collaborations with university, including modeling, Dr. Pooja Gudat, Professor Peter Slater, and that's participating to making Exonaut 3 better and better. We are also working on next generation products that will come online in a few years. Another scoop I wanted to announce today. I think developing a product is very difficult, but it's only part of the story. Scaling up is something else, and here I think we're very lucky to have the support of CBMM. So here we're announcing a multi-year manufacturing partnership with CBMM. So CBMM is building a 2,000 ton per year facility to supply niobium oxide anode grade to be applied in Echion's XNO from Q1 24. So the picture here is a picture of the CBMM site in Araxá, Brazil. So we're very excited by this manufacturing partnership. It's commercially it's very important to be able to look at the customer in the eye and say, yes, in 2024 you'll be able to access 2,000 ton per year of material. We'll know the cost, we'll know the quality, we'll know the ESG impact and all the commercial terms. So that's great, and we're very excited about that. It reinforces as well a long-standing partnership between Echion and CBMM. So CBMM is a shareholder of Echion. So this 2,000 ton per year, available from Q1 24. XNO is already produced at the multi-10 ton scale. So this year we've probably done about 10 ton of XNO and sold to customers. On that, here's a picture of half of the team. We are based in Thorsten, which is a 20-minute drive south of Cambridge. We have a full team of material scientists, electrochemists, and application lab to support our customers, the cell manufacturers, and help them develop the best cells as soon as possible. Very keen to engage with you all later tonight. Thank you.
Wow, brilliant! So a couple of scoops there, John. That's excellent. And getting to the point where you've got materials available when you've been in development, that is really important. So congratulations on that.